Okay, I think we will go ahead and get started. Hi, everyone, and thank you for joining today's lecture. My name is Brittany DiLoretto with Manatee Lagoon, and today we are hosting a very special lecture in partnership with Florida Atlantic University's Frontiers in Science Public Lecture Series. For those of you who haven't been to Manatee Lagoon before, we're an eco-discovery center in Riviera Beach, Florida. In addition to being a great manatee observation spot during the cooler winter months, we also have interactive exhibits and family-friendly programming offered year-round. We are very excited to be able to still offer this joint lecture virtually today, where we will hear from special guest Dr. Marianne Porter. As you listen to today's lecture, please feel free to submit your questions in the comment box, and we will save some time at the end of the lecture to address these. Now I would like to introduce our speaker today. Dr. Marianne Porter is an assistant professor of biological sciences at Florida Atlantic University. She is originally from Arizona and received a Ph.D. in biology from the University of California, Irvine. Her research has taken her from the Grand Canyon studying native plants along the Colorado River, building autonomous robots to study evolution, and now she is based in Florida studying biomechanics of marine animals. Dr. Porter joined the faculty at FAU in 2014 and founded the Florida Atlantic Biomechanics Lab, where she is currently training 4 Ph.D. students, 1 master's student, and many wonderful undergraduate researchers. Current research in her lab includes understanding shark skin stretchiness, lionfish spine puncture performance, and examining sharks swimming using 3D techniques and in the wild. Please join me in welcoming Dr. Marianne Porter.
All right, thanks, Brittany, for that introduction. Can you all hear me? Yeah? Okay, great. Let's see if I can change. Here we go. So my title slide. Today I'd like to talk to you about some of the work that's being done in my lab, the FAB Lab, Florida Atlantic Biomechanics Lab here at FAU. And it's a real pleasure to present to you today because I peeked in on the participants and I see some of my colleagues from around the nation watching, as well as some of my undergraduate researchers who have had to go home because of the COVID virus, and some of my grad students that I haven't seen for weeks now. So it's really exciting to be able to see you all, even in this virtual space. So with that, we're going to talk about tuning fish, mechanics of biomaterials, and changing demands of locomotion. And actually, this is a title that reflects one of the things I'd like to do by the time I retire. And I'm going to show you some of the pieces of that puzzle that we've been putting together in my lab. So first off, here's our newest lab icon that was actually drawn by one of my undergrad researchers. We've got our shark here, and we've got a vertebra to represent the biomaterials that we study, and the shark skin, those really cool denticles or the little teeth that make shark skin feel like sandpaper. And what I like to do in my lab is really think about how these materials are put together, how they work individually, what happens when you put them together as a functional system, and how that translates into movement or locomotion in the animals that I like to study, sharks. All right, so today in this talk, I'm going to talk about 3 sections of my research that have been going on actively over the past year or 2, thinking about skeletal elements, so talking about some of our recent work in this area, a method that we've helped innovate in my lab, thinking about how animals swim in 3 dimensions, and then finally studying swimming in the wild. So a lot of what we fish work is really based on what we have seen in lab experiments. And here, because we're lucky enough to be in Florida, even though we can't go to the beach right now, we still have access to some beautiful clear water that I will show you, and some amazing opportunities to study these animals swimming around in the wild. So first up, we're going to talk about skeletal elements. And again, we're focusing on sharks today. Don't be a little confused, because this is my PhD student, Danielle Engel. She works at Manatee Lagoon, and here she is posing with a dolphin that is hung as a display piece in the College of Science, one of the College of Science buildings here at FAU. And Danielle has really been focused on her dissertation working on marine mammal bone. But when she first came to FAU, I helped her get her feet wet, as it were, in studying biological materials by having her work with me on some shark cartilage. So I'm going to present some work that she did when she first came to my lab. So here we have an X-ray of a horned shark. This is one of my radiographs that I took of a horned shark, a shark that we can find in California. I really love this picture because you can see very well the horns on the shark, the two spines coming up off of the dorsal fins. You can see these really heavily mineralized jaws. You can see the little dots all over the skin representing those denticles, that mineral on the skin. And right through the middle of this animal, you can see this lovely vertebral column, all these repeating elements that basically, as they wiggle around, translate into the motion of different animals. So what do we know about this cartilage so far? Well, we know that cartilage is really stiff and strong. And what does that mean? That means if we look at it as a material, the way an engineer would, it's really similar to bone in a lot of ways, even though it's fundamentally cartilage. And so the best way to highlight this is for everybody to kind of take their finger and wiggle their nose and wiggle their ear. That's what we really feel and think about when we think about cartilage. But in these sharks, they're going to make up the entire skeleton. So it's really useful to be stiff and strong, not super squishy and wiggly. If you had a squishy and wiggly skeleton, it would be really hard to effectively move around in the water. What else do I know about this vertebral column? Well, I know that each of these individual little vertebrae can act like a spring. They can compress as the animal is swimming and then return to their original shape. So this whole vertebral column is working together as a bunch of little springs put together. And this makes me think that these vertebral columns can work to store and return elastic energy as animals are swimming around in the wild. This is useful. Some of our other work showed that sometimes these can behave as brakes. So this is a really great and dynamic functional system to study. One of the limitations, or one of the things I didn't know, was a little more detail about this. So all of my studies so far had really focused on the vertebrae right under the first dorsal fin, so right under the first big spike on this shark. I knew a lot about the vertebrae there, and I assumed the rest of the vertebrae would be pretty similar. But maybe not, and I'll tell you why later. I also know a lot about these vertebrae when I test them to failure. And so what that means is when I do experiments on this cartilage, I smash it until it breaks. If anybody's feeling a little overwhelmed or anything, stop by my lab. We've got a wonderful machine that we can smash things with. It's a great way to get out some of your frustrations. So when we open the lab back up after coronavirus things, stop by and I'd love to show it to you. But what I know about this cartilage, I know from smashing it completely. That gives me a lot of information about this material, but it really doesn't give me a lot of information about how this is working in a shark as it swims. Because a shark, as it's swimming along in the ocean, is not going to be breaking its skeleton with every tail beat. So that's another limitation of what I don't know so far. And another thing I didn't know was how shark size impacts the way this cartilage works. We know that our skeletons that are made of bone change from a tiny kid or a fetus and embryo developing into an adult. Our skeleton is going to change very dynamically over time. But we don't know if there was an impact on size of the animal with this shark cartilage. So the study I'm going to tell you about now, we were really interested in looking at a few things. First, does it matter if you're a small, medium, or large shark? So does being a baby shark matter? And hopefully you all have that song in your heads now. Another question I wanted to know was, are there differences between this front head end of the vertebral column and the back end of the vertebral column? And I told you I only had studied vertebrae previously under the first dorsal fin because that's what I had access to. But really, I was thinking there was going to be a difference along the length of the vertebral column because the back end of the shark needs to be able to wiggle in a different way than the front end of the shark, because that's where we're going to be producing a lot of the thrust that helps the shark swim forward. So it's going to be that force of the shark pushing against the water that allows the shark to move forward. Another goal of this project was to squish the vertebrae just a little bit so we could compress them the amount that we would expect them to move when they're actually swimming around in the water. And the last thing I wanted to look at was, because I could look at multiple species in multiple size ranges, is the way that this mineral is arranged, we can see the mineral here, does that matter? And so if we look just at our vertebral column here, we can see in this example, we've got a nice kind of hourglass shape and we've got some struts in the mineral, but this is going to change very dramatically among species. And so I really thought the way that this mineral is arranged is going to be important for telling us about how this cartilage works. So what Danielle did was she was able to get 6 different species, and she took individual vertebrae out of the vertebral column along the whole length of the shark, and she took her individual vertebrae. We're going to reorient it. This is the way it is in the shark. Here we're orienting it now, and in the middle, you can see what it would look like if we were staring at the head of the shark, looking at it. And the hole in the top here is where the spinal cord would travel in this neural arch. And what she did was she smashed it. Remember, I said one of the things we do really well in my lab is we can smash things. So here we have an actuator that's moving down against a plate, and our little vertebra is being smashed. And we're looking at how the mineral is compressing in the vertebra as we go through space and time during this test. Okay, so what did I find? Well, does it matter to be a small, medium, or large shark from a variety of species? The answer is yes. Just like in human skeletons, where our skeletons are changing over time, little sharks, baby sharks, seem to be better at resisting deformation and absorbing energy compared to bigger sharks. And this might be a trade-off with just body shape, because little sharks have a very different shape compared to big sharks. If you've ever been out scuba diving and you see a small shark, they're oftentimes much skinnier than a large shark. The example I'm thinking of in my head is a giant tiger shark. They get quite girthy as they get bigger. But the little ones are kind of pretty skinny. So size does matter. Those little sharks are better at resisting deformation and absorbing energy. Well, what about if I look at the front half of this vertebral column compared to the back half of this vertebral column? We did find a difference here too, which was really exciting. So the vertebrae from the back end of the shark are in fact stiffer. And this was exciting because I didn't know this. I had only looked at vertebrae from this region under the first dorsal fin before. And so to be able to show that there is a difference between the front end and the back end really gives me a lot of information that I can use when thinking about how these animals actually swim. So remember, these are all individual little springs, but our springs are going to get a little bit stiffer in this back end as we're trying to generate thrust and have our shark moving through the water. So that was a really exciting finding as well. Remember the last thing I said that I really wanted to know about this study? I wanted to know if the mineralization pattern mattered. And so when we were squishing them, we were looking at just these angles here labeled angle 1 and 2. And we did find that the angle or shape of this mineral within the cartilage really does matter and impacts the material properties like stiffness and toughness. But this is a really crude measurement, right? I told you some of this mineral is really dramatic and there are some very interesting arrangements of it. So here we were just looking at these very crude angles. What we're working on now is to really get an idea of how this mineral works. So here are some really gorgeous CAT scans or CT scans of shark vertebrae from 3 different species. On the top row, you can see the whole vertebra. And in the bottom row, you can see a section of about halfway through the vertebra of the melted away mineral. And you can see that there are very different arrangements of this mineral that may be impacting the way this cartilage works. And so this is some of our current work. Like I said, we were able to use that crude measurement where we could look at just the two angles, and that told us a lot about how this mineral impacts the material properties, like the cartilage's ability to resist bending or compression. But now we're able to use some high-tech technology. So anyone in the audience who has gotten a CAT scan before, this is the same technique we're using here on these little vertebrae. It's a much smaller machine though. And so this opens up an amazing collaboration that we've started with the ALS Imaging Lab at FAU High School. So they have this great equipment over there at the high school, and we're able to go there and collaborate and get some amazing digital anatomy from this cartilage. And now we're able to really start to look at how the arrangement of this mineral will impact the material properties. And to give you an idea of why I'm so excited about this, the first set of vertebrae is from a blue shark, the middle set is from a hammerhead shark, and the set on the right is from a short fin mako, which is one of my favorite sharks in the entire world. And you can see why. The arrangement of the mineral is in these different plates, and it is really interesting how it's arranged. And this is very similar in sort of the cousins or closely related species of mako. So I'm really interested to see how this works. And like I said, we're just starting to be able to look at the arrangement in this amount of detail. So I'm gonna have to report back in a couple more years what's going on here. But we've been able to learn a lot through Danielle's study. So that's the skeletal element aspect. Now I want to start to show you a little bit about how we've been innovating the way we can study swimming a fish in my lab. And so the first step in that is moving from 2 dimensions to 3 dimensions. And this is going to really highlight the work of Dr. Sarah Hoffman, who got her PhD in 2019 from my lab. So here's Dr. Hoffman and one of the bonnethead sharks she studied. And her work was featured on the cover of Experimental Biology in 2017. So what was Dr. Hoffman interested in? Here, we've got little baby hammerhead sharks swimming around in a pool. One of the things I like to do when I study swimming is look at sharks cruising around through a pool. I know that some of my swimmer friends have logged in and they're probably very jealous of these sharks being able to swim laps right now because we can't. Here we have these sharks swimming. They're swimming the speed they want and the way they want. Many experiments use flumes like a water treadmill, or the dreaded tethered swimming where you tie a fish up and let it try to swim. This is what I have been doing for the past several weeks in my pool. It's not pretty. It allows me to swim, but it's definitely not the speed or the way I prefer to swim. Same with a flume. If anyone has ever gone to the gym and gotten on a treadmill, you choose the speed of your treadmill. You don't let your gym buddy choose the speed. They might choose something too fast. They might choose something too slow. You don't want to risk it. You could fall off the end of the treadmill and it would be bad. That's one of the drawbacks I see to flume studies. We can learn a lot about how an animal swims, but as an experimenter, we pick the speed. So what we've been able to do in my lab is study animals in 2D. So we can put cameras overhead and we can study these fish swimming. Now, as these hammerheads are swimming by, they are basically an infinite number of points. If we wanted to track the points of this animal, it would be really hard to track every space or every pixel through time. Not impossible, just a lot of work. One of the things we like to do is decompose their shapes into different sets of points. And this allows us to take an animal that's composed of millions of points and put it into few key points or areas of interest. And so we can look at regions of the body, like the front end of the back end, and we can look at the tip of the tail if we want to get tail beat frequency and tail beat amplitude. So we can learn a lot about a fish doing this. We can see the velocity of their swimming. We can measure their swimming efficiency. And in this particular study, we were able to learn that bonnethead sharks flex their body with a greater amplitude. So they're waving their bodies back and forth more than a hammerhead. And a hammerhead is going to flex its body at a greater frequency. So the hammerhead is going to wiggle faster as it swims. And when we break their body regions up to a front end and a back end, we actually find that they're moving at different frequencies. So they're operating as a double oscillating system, which is a little weird, and we haven't quite figured out everything that that means. But we're able to get this great view and understand what the shark's doing from the top down. Now, what Dr. Hoffman was really interested in is maneuvering. So during maneuvering, we can look at sharks swimming and turning from this overhead video and understand how they turn from just this view. But if you've ever watched a shark swimming around a tank in an aquarium and they go and they turn around a corner, it kind of looks like they're using their pectoral fins. And a lot of what we know about pectoral fins in swimming comes from flume experiments. So these are the pectoral fins. Those would be kind of the fins that come out of the short shoulder girdle of the shark. It's very hard to use my interpretive dance about my research on a screen like this. So we've got our pectoral fins here. And a lot of what we know comes from flume studies where we can say the shark is swimming faster, the shark is swimming slower, the shark is angling up and down, but we can't get it in maneuvering. So what Dr. Hoffman developed is what we call VROM. So looking at moving morphology, video reconstruction of moving morphology. Now, these are not sharks. These are human actors. One of the ways that this technology has been used in the past is to, if you look here at our actors on the left, deconstruct our actors that are, millions of points to just the dots on their little suits. And then with our computer programming, we can make those dots clouds in space, as we see in the middle here with these blue dots. And then we're able to connect the dots and create these coordinate systems. And these coordinate systems give us a really simplified view of this really dynamic three-dimensional shape. And then once we have our stick figures, we're able to create our 3D models to get an idea of how animals are swimming. So this has been done in movies. I hear Matrix 4 is coming out sometime soon. If anyone's seen a Matrix movie, you probably know what I'm talking about, video games. And we can use it in research, but oftentimes we're limited by the size of a fish or animal we can use because we need to have a highly calibrated volume to work with. So what Dr. Hoffman did was she really tried to innovate this method in using it underwater. First off, anyone who works with electronics knows that moving your experiments underwater is a problem because electronics underwater gets dicey. And so what she was able to do was create a system that uses GoPro cameras, so consumer grade equipment. You can go to Best Buy or order online from Best Buy and get your GoPros. And she was able to use these GoPros to film these sharks swimming around. So here we have a bonnethead shark that turns into the screen and comes at you. You can see that the bonnethead shark is wearing a bunch of little dots on it, just like our movie actors. You can see that there's a ruler on the ground so that we have the ability to kind of calibrate one surface of our cube, which is denoted by these 4 little pieces of coral here. So they form a square on the bottom of the tank. And if you imagine each cube, each coral head going up to the surface of the water, that creates this volume that we're working in, which is the volume that our bonnethead is moving around in. And we've got our little broom that we help convince the bonnethead that it wants to swim through our area. Now, one of the questions I always get is, does putting the dots on the shark hurt them? Well, let me tell you right now, because I don't want you to be concerned about the shark for the rest of the talk. To put the dots on the shark, we lightly anesthetize the shark. We glue the dots to its body. This process took about 1.5 to 2 minutes. And then we put the shark back in the water and it would swim away. So remember at the very beginning of the talk, I told you sharks have those little teeth on their skin that make them feel like sandpaper? Well, the teeth on the skin also help prevent the little dots that we put on the shark from bonding very closely to the body of the shark. So these experiments only lasted a few hours because after a few hours, all the glue started to wear off and the sharks were losing dots in the tank and our experiment was over. So just to tell you that so you're not concerned about the shark. Everybody always asks that question. So we have our bonnethead shark swimming through space. What happens next? Just like in the movies, we connect the dots. So we're able to create these coordinate systems. Here's another species we've worked on with this project called a dogfish shark. And we've got our reconstruction software that we use here on the right-hand side of the screen. So while we were using GoPro cameras that anyone can use, another powerful aspect of this method is we were able to use open source software. So free open source software, consumer grade video equipment to do these experiments. So they're really accessible to scientists around the world. So after we connect the dots, we can work through our program and develop the 3D models. So here we have our 3D model of our shark swimming through space and our dogfish shark in the background. We can remove the dogfish shark and just see our animated shark moving through space. And if we really wanted to know how that pectoral fin was moving during a turn and give us an idea of how these sharks are able to maneuver, we can hold our shark still and just look at the movement of the fin. And that animation looks like this. So now we have the fin moving around. It's kind of bouncing around, it's a little sped up here. But what we've been able to learn from these studies is the bonnethead shark that you saw at the beginning will put their fin down. They'll depress their fin, kind of drop it a little bit like a speed skater, and speed up through a turn. And the dogfish shark is going to drop their fin, but also sweep it forward a little bit when they do a turn. So these sharks are using different strategies in the way that they're maneuvering their bodies as they're moving through space and navigating complex environments. So why would anyone care about this? I think my parents might be watching. So if we're wanting to think about how to maneuver through complex environments, we can use this information to build better autonomous designs or vehicles. So one of the things we might want to do is navigate or use surveillance to study coral reefs over time. We've got coral reefs here in Florida, and anyone here in Florida today knows that it is really hot, and it's been really hot. So we're projected to have a wild hurricane season. Maybe we wanted to know how that hurricane season is going to impact our local reefs. So if we wanted to build autonomous vehicles to go out and keep track of the health of these reefs and the shape of these reefs, we could do that, and we could build autonomous vehicles that could really maneuver through that complex environment. All right. So that's shark swimming in 3D. The last thing I wanted to tell you about today was swimming in the wild. So for my swimmer friends who are listening, it's all well and good to swim in the pool. That's a ton of fun, especially right now, we miss it a lot. But one of the best things is to be able to go to the beach and swim around in the water. But it's a little hard to study animals in the wild. In the lab, you at least have them in an enclosed space so you can keep track of them, you know where to videotape. A shark in the ocean is a lot harder to find and study, especially if we want to get that video from above, like we saw in those hammerheads swimming in the tank. But here in South Florida, we have a pretty unique opportunity every year. So many of you may have heard of Dr. Kajura talking about the blacktip shark migration. So every year in Florida, These blacktip sharks are going to migrate, and they aggregate here in South Florida. And Dr. Kajura has been able to find really large groups, sort of between Miami and West Palm Beach. Here's part of his flight plan, flying up the coast. So we have a lot of sharks here. We have some really shallow and beautiful clear water. So what I wanted to try to do, by now you've probably gathered that I like innovating methods and trying new things. I wanted to see if I could study how sharks swim out in the wild. So when I was recruiting grad students, that was one of my big questions, looking for good students. And then my question was, hey, can you fly a drone? And this is how I found Braden Ruddy. So he is one of my current PhD students. Here's him flying the drone. He has the rough graduate job of going to the beach with the drone in the mornings and looking for sharks in the water and videotaping them. So how do we do this? We want to be able to get video that we can analyze, just like we did the video of the hammerheads at the beginning of this talk in the lab. We want something of that quality. So can we do this in the wild? Well, Braden takes his drone to the beach and videotapes the sharks. So many of you who have seen Dr. Kajura's talks may have seen some of the aerial footage. Here's one of the stills from his work. You can see all the black spots in the water here are these sharks. They're near shore. The water is very clear, it's very shallow, and easy to see these sharks in the water from an airplane, and even easier if you're flying a drone much closer to the water. And here you can see our humans on the beach enjoying their morning walk by all of these wonderful sharks. So here's a view of the beach. What does it look like when we actually have the drone up trying to collect data? So remember the video of the hammerhead shark swimming in the lab in that round tank. Here's a blacktip shark swimming through the frame for us. We've got shallow, clear water. The shark stands out beautifully against the sandy background. And we can see the shark to be able to add a bunch of points to its body and understand the way it moves, much in the same way we've always been able to do with animals in the lab. So we can do this with one shark swimming by. But we're out in the wild, and we've got a giant migration or aggregation of sharks that are hanging out here. So what do we see when we put the drone up and collect some video data? Well, we see many sharks. And so we know that sharks are able to swim in large groups, and now we can describe the movement of the sharks individually, but in also many group sizes. And we can think about how all of this water washing around off the caudal fin of these sharks is impacting the shark right behind it, the shark beside it, and get an idea of how these animals are working in groups. And this is work done with Dr. Sid Burma's group in the Ocean and Mechanical Engineering Department here at FAU. I saw him online as well, so hi Sid. So we're looking at the flow of these fluids moving through space and how they're going to affect how sharks swim. So we're able to put the dots on our shark and think about the speeds of individual sharks. We can look at how they turn. So just like when we were looking at maneuvering, we can think about how these animals are moving through space when they need to maneuver. We can look at speeds in different group sizes. And from what we know from theory, thinking about this as a two-dimensional problem, we think that groups of 4 sharks should be the most efficient shape in terms of losing all the water off the back end of the shark, so those little vortices that we saw in blue. And our early data are showing that this might be true for these sharks. A group of 4 might be the most efficient way to travel. And so we're able to look at this again, in these animals swimming in the water. So in the wild, this isn't a shark in a tank. Here's some video taken from one of Dr. Kajura's block cams, and we can see this group of sharks swimming at us. We can see how shallow this water is. We can see how clear it is and how easy it is to see these sharks. So this is our in-water view. And you can start to get an idea of where these sharks are swimming in relation to each other and what they're doing. And so we'll have more of that work coming out in the next couple of years, but we've already been able to learn a lot in terms of these groups of 4 are potentially going to be most efficient, just like we would have predicted from animal behavior theory. The last thing I want to show you today is an extension of this project. So while we're able to study the sharks swimming around in the wild, these blacktip sharks swimming by themselves and swimming in groups, we also see other things happening by the drone. So here we have a hammerhead shark. Remember, we were able to study the hammerhead shark in a tank, and that was just a baby hammerhead shark. We could study it swimming around, and it was a little guy, one that could fit in the lab. Here we have an animal that's probably in excess of 12 feet long, swimming around and going after these blacktip sharks. So you can see this aggregation of blacktip sharks moving away from this hammerhead. This is an amazing piece of this project because now we can look at how individual sharks, individual blacktip sharks are swimming. We can look at them swimming at different speeds now that they're swimming a little more motivated because they have this hammerhead near them. We can see how they're swimming in groups and how they maneuver to evade predators. And so you can see all of this and learn all of this from these blacktip sharks. In addition, we've only been able to study this hammerhead species swimming in the lab, but now we have the opportunity to look at how these animals are swimming full grown and in the wild. And so we can get ideas of how this animal is swimming. You just saw it maneuver right there. It could do this very tight turn. Here our chase scene gets a little wild. You can see the dorsal fin of this hammerhead coming out of the water, which tells you how shallow this water really is. And here comes a blacktip heading onto the beach to avoid this hammerhead shark. So we're able to use this video to understand both of these species on their own, but also observe and quantify predator-prey interactions in ways that we've never been able to do before. So that's some of the exciting things that are going on now. So with that, I'd like to thank the National Science Foundation, the Save Our Seas Foundation, and the Colgan Foundation, who generously support our research. We work with many federal agencies and state agencies, including FWC, so Florida Fish and Wildlife, the FAA, and also NOAA. Much of our work, especially with the blacktip shark migration, happens with the FAU Shark Lab. And of course, we always like to thank FAU. This is an ideal location and opportunity for us to do these really cool and innovative experiments. And then finally, my graduate students are funded and supported by a number of societies who also generously support students, and we really appreciate that. So with that, I will put it back to our hammerhead chase scene because that's everybody's favorite, and we can take some questions. So thank you all for logging in. I hope you're all staying healthy and well. Oops. Let's see, the Q&As. All right. So from a 9-year-old, what's the biggest shark you've worked on with your models? That is a great question. So I think the biggest shark I've worked on would probably have to be this hammerhead shark now that we're getting video of it. Most of the sharks we work on in the lab are only about 1 meter or 3 feet long at the biggest because, you know, I don't want to have giant sharks in the lab. That would be really expensive to feed them, and we don't have tanks big enough to hold them. So probably these hammerheads are the biggest ones that I've been working on now. In terms of sharks we've dissected, some of our work on the vertebral columns, we have worked on really big adult bright white sharks, which is some of the favorite sharks to dissect because I grew up watching Jaws. So that's always a really fun dissection to do. One of the other questions is, what are some of the selective pressures that might shape cartilage density variance that you observe between different species? That is a great question. And so some of these mineralization patterns were first published about and really talked about in like the 1920s. And they discussed that there are different morphology patterns. And there hasn't been a lot of work done on it since then. So in terms of selective pressures, I think it might have to do how different species swim. So remember I showed the mako had all those little plates of mineral in the cartilage and it was so pretty? Well, I always thought that mako sharks would have the stiffest and strongest vertebrae because they're the fastest swimming sharks. So I thought they needed to have bodies that would be very, very stiff. And I thought that that stiffness would basically scale down from the whole body right down to the vertebral column and the individual vertebrae themselves. But when I test mako vertebrae, they're actually pretty wimpy compared to other shark species. And so I think that that species has a really strong morphology, a description of their musculotendinous system. So they've got tendons that basically transmit down the whole body to help move forces from the front of the shark to the back. So basically they're arranged with their muscle and tendons, helps them be very stiff. And so I think in terms of selective pressures, I really focus on the cartilage, but this is obviously cartilage, muscle, tendons, and skin that are going to be impacting whole body stiffness, and it might just depend on different species and kind of what their goals are in life. Another question, what are some of the unique inventions that have come out of research like this, like the shark skin? Yeah, so one of my students is working in the FAU Tech runway, and she's working on some innovations with shark skin that are working through the patenting system. So I will let her talk about that in some other talk. In terms of what we've learned about shark skin in my lab is shark skin is stretchy and it gets a little bit stiffer when you add the denticles or that little armor to it. And so an application of just that little data graph would be thinking about making flexible body armor. So you can make flexible body armor with tiny little pieces of mineral or tiny little pieces of something hard that would add to the stiffness and overall flexibility of it, but still allow for flexibility. So if someone wanted to wear it. Next question is, when is the migration period of the sharks in Southeast Florida? So we're just wrapping up the shark migration. The numbers start to increase through January. So the sharks usually start to arrive down here in January. A lot of the largest aggregations have been documented in February. And then the numbers start to decrease through March and April. The numbers start to get a lot lower. There are resident blacktips that hang out here all the time. So this large migration comes in and then they leave. But there are still always blacktips around, so they're always here. Some of them are at least always here. And another question, did the small shark know that the larger shark would not be able to follow it into the shallow water? What these sharks know and don't know, we can only imagine, but these sharks have a lot of sensory systems. So I study how they move, but these sharks are going to have all the senses we have, plus they are going to have electroreception. So these sharks probably have evolved strategies to know what they're able to do and what they're not able to do. And so they probably, because it's much smaller, felt comfortable with using its lateral line and vision and electroreception and going into shallower water than this hammerhead, which is much bigger. It probably didn't want to go as shallow as some of those other smaller sharks. Right. Those are all the questions in the little Q&A box. Are there any others? No? Let's see. I can't see if there are any other questions popping up. Oh, here's one. Oh, great talk. Thank you. All right. Any other questions? Everybody just loving watching this hammerhead? Probably one of my favorite things to watch too right now. All right.
It looks like there may be one more question that just came in.
Okay.
There's a question that says, why do some sharks migrate and some don't?
Okay. Yeah, why do some sharks migrate and some sharks don't? That's a great question. So with the black tips, some of them are going to be resident, some of them are going to migrate. We know that the ones that migrate seem to follow a temperature signal. So it might have to do with what their preference is. And the sharks that live locally may tend to go to deeper water when they need to get cooler. Those are great questions that I don't know the answers to right now. Are students allowed on the beach currently with the restrictions due to COVID? That is a great question. And no, they are not allowed on the beach currently. We do have some field work going on, and those exceptions have all been run through the proper channels, but it is very limited in general. I have made the decision to basically close down the lab for the moment because several of my grad students are writing their dissertations, so they're happy to be at home writing, and a couple of my students are taking a pretty heavy course load this semester, so it just made sense for, as we finish off the semester, to have the lab closed. Depending on how this continues, we will have to make decisions in the lab with the department, with the College of Science, and with FAU and all local and state authorities if we decide we need to go out and do field work. But mostly we're staying home. I am actually at home right now. So, you know, if you hear people talking in the background, that is my 6-year-old. Yeah, that's a great question, but we're mostly hunkered down. Is the hammerhead chasing the blacktip shark for food? That's a great question. Yeah, these hammerheads eat these blacktip sharks, and there is some video out there of them catching the blacktip sharks, which is also very dramatic, but I don't put that in public talks because sometimes it sketches people out. So I put the hammerhead trying very hard, but not being successful. But yes, these hammerheads do eat the blacktip sharks. All right, any other questions from Facebook or anything? Let's see. Oh, did the shark ever catch a fish? I don't know if this one ever caught one. I don't think it did. It's a great question, but we do have some video of when they catch it. So do you guys know if there are any questions on the Facebook feed? Let's see.
Not any new ones.
Okay.
All right, then I think we're good. I don't see any new questions coming in. Oh, there's one that just popped up.
Let's see. Have you ever calculated caloric expenditure? That's a great question. I have not. There are some amazing physiologists who think a lot about the energy that these sharks are needing and requiring to do their migrations and swim around in general. And so some of those calculations are based on information people get back from tags. When sharks are tagged, you can get some of that information and make those calculations, but that's kind of out of my, I just study how they wiggle and swim around mostly. Oh, the blacktip sharks seem to be communicating with each other. How do they do that? Well, sharks are going to be able to sense where they are, so they're going to have vision, so they can see where their neighbors are, and they're going to feel that flow of water around them using their lateral line system. So those are the ways they're very easily communicating with each other. Plus, they've got electroreception, so they can see, basically feel where their neighbors are in this group and work to stay away from the really big hammerhead.
All right, well, I think that's it. I don't see any new questions that have come in. So thank you, Marianne, for giving this wonderful lecture. And thank you everyone for tuning in.
All right, thank you for organizing, you guys. And I hope everyone stays safe out there.
You as well. Have a great weekend, everyone.